Hi, welcome to the video solution for Edexcel past paper. This is Edexcel IAL Physics Unit 1 January 2021, and this is the second video of the series. So let's start. Question number 16. A steadily increasing tensile force was applied to a sample of a titanium alloy. The sample had an original length of 40 centimeter. This is original length L, and the diameter 5.05 millimeter. This is diameter. State a suitable measuring instrument to measure the diameter of a sample. A typical question about measuring of diameter of a wire, and the instrument that we use to measure the diameter of very thin object or diameter of a wire is micrometer screw gauge. It's 1 mark, so you just need to give the name of the instrument. The graph shows how stress varied with strain for the sample. Okay, this is a stress in megapascal and strain graph is stress strain graph. Remember, stress is in mega, million pascal. Determine the Young modulus. So Young modulus, if a stress strain graph is given, this is a stress sigma, and this is a strain epsilon. So Young modulus is a stress divided by strain, and in this case this Young modulus y is equal to gradient of the linear section of the graph. So we need to choose a linear section of the graph, and we find the gradient, and that gradient will give us the Young modulus. And for me, I think in this section, if you see, the graph is slightly bending right side. So for the safe side, I will choose this point, meaning 600 stress and corresponding strain. So if I choose this point, that means the gradient is y2 minus y1 divided by x2 minus x1. So this value of the point, this is y2 and this is y1, and corresponding value is this is x2 and this is x1. So you can say that y2 minus y1, 600 minus 0, but we have a million, so 10 to the power 6 into divided by strain. And if you see, this is 0.01 and this is middle, so 0.005. So 0.005 minus 0, and clearly if you divide, you have gradient is equal to 1.2 into 10 to the power 11, and gradient is Young modulus. So Young modulus y is equal to 1.2 into 10 to the power 11 Pascal. This is Young modulus. The sample broke at point B. Where is the point B? If you go back, this is the point B where sample is broken. Determine the force required to break the sample. Of course, if you see, you have a stress at which the sample broke. This is the stress, and we need to find force. So the idea is, in general, force is stress is equal to force upon area. So force would be equal to stress time area, and this stress is a breaking stress that we can measure from graph. So we measure stress from graph, and then we can put the stress here and multiply with the area. So if you see, this is the stress at which the wire broke, and this is 1200 and 40. So this is 1300, this is less than 1300, and 0 to 200. So one line is read as 20. That means 1280 greater than 1220. Let's take it 1290. So this value is 1290 million Pascal. This is breaking stress, and we use this stress to multiply with area to find the force. So now F is equal to, stress is 1290 into 10 to the power 6. This is stress times area, and this is wire, and area is pi r square. So remember, area of a wire, we have a choice. We can do area is pi r square, or you can say pi d square by 4. I'm comfortable with this formula because I just want to avoid a step. So I can put directly diameter, because r is equal to d by 2. So r square is equal to d square by 4. So that's what I'm doing, pi into diameter. And if you see, the diameter was given as 5.05. So, but it is in millimeter. Now, so pi 5.05 into 10 to the power minus 3 whole square. This is diameter square divided by 4. Now you put every number in your calculator. So force that you will find after simplifying is 25838.2 Newton, or you can say 2.6 into 10 to the power 4 Newton. That's how you can figure out force at which the wire breaks. Part 3, the graph below shows a linear section of a stress strain graph for the sample. Show that area under this graph represent the work done per unit volume in stretching the sample. So basically, stress strain graph, and if you find area under the graph, in fact this area is work done per unit volume. That's what we need to show, that energy per unit energy stored per unit volume or work done per unit volume, and we need to prove that area is work done per unit volume, or remember, work done is energy. So how do we start? First write the expression for the area, and this is clearly a triangle. As per graph, area A would be equal to half of base into height. In this case, base is strain. Let's make it sigma. Epsilon. This is a symbol for strain, and this is a stress. So half of epsilon into height, which is stress. Now half of this epsilon is change in length delta L upon L. Change in length per unit length into stress, force per unit area. Now clearly it's a product form, and clearly you can see that F into delta L. This is force into extension, which is work done. But if you recall, work done is not F delta L, but half of F delta L. So I am rearranging this equation as, watch carefully, half of F delta L upon A into L. Clearly, half of F delta L is equal to work done divided by A into L, area multiplied by length. This is volume. So area is work done per unit volume. It is not mandatory that you do all the steps. You can skip one or two steps of your understanding, and it's your choice. So that's how you prove. This is area under stress strain graph, which is work done or energy stored per unit volume. So you also can say that A is equal to energy stored per unit volume. And if you remember, this is called also be known as toughness of the material. Okay, but this is just additional information. This is sufficient for this part. Question number 4. The area under any stress strain graph represent work done per unit volume. Okay, estimate the amount of work required to break the titanium alloy sample. So to break, work done to break. So that means we need to consider the whole graph, and we need to look at the graph. So in order to find the amount of work done, so we need to find area under the graph. So there are many options. The one option is you can count all the squares, like you can, this is, slightly time taken. So you can count all the squares, like this. And then after counting all the square, you find, you multiply number of squares with the area of one square, so you can have a total amount of work. But because this is a special type of curve, I'm just giving you one more technique, which is also valid. What do we do? Instead of counting, you can try yourself. Okay, I would recommend you must try after counting, counting method, counting square, and then find the area or estimate the area. But I'm giving you another technique, which is finding the area of a rectangle after drawing suitable horizontal line. So you need to draw a horizontal line with the help of ruler, and that's the way. It's all about practice. You need to choose the position on your own, so that you can have a right area. The idea is, suppose it's just an example. If I draw a horizontal line at 600, it's just a random position I'm choosing. You draw a horizontal line till the point B, and then you can see you have a rectangle. I'm sorry, I cannot draw a straight line in this. I do not have any option, but it should be a straight line with the help of a ruler. So you see you have a rectangle here. But the idea is simple. We need to find area of this rectangle only. But whether this is a suitable rectangle or not, this is the important question. So the thing is, if you see, I am in this rectangle, I am including some external area, this much. And I am excluding some required area that should be in my calculation, this region. So I am excluding. This is excluding, and this is including. And of course, excluding area is much larger than the including area. So this is not a good choice. So this position is not a good choice. So the best line is, I guess, if I choose this position, watch carefully. I draw a horizontal line at this position, and clearly I make a rectangle. Again, I cannot draw a vertical line in this slide, so but you must use ruler. So you must have a rectangle here. So this is your rectangle. Now watch carefully. If I find area of only this rectangle, the whole big rectangle you see here. Now area in this rectangle, I am including some area which I do not need in my calculation, but I am excluding this area. And if you see by eye, these two areas are same. So if I am excluding the needed area, in place of this I am including this area. So this area will compensate what I am losing. So area of this whole rectangle will be area under the graph that I needed. So I just find the area of the rectangle. But remember, if you are using this technique, you have to show the rectangle with the correct line and the number. So this number is 1012 and 1100. 1100, and this is 0505556. So you just length multiply by the width. So area A would be equal to the length. Length is 1100, or height, whatever you say, 1100 into 10 to the power 6 times the breadth or width, which is 0.056. If you multiply, so area would be equal to 61.6 into 10 to the power 6. Remember, this is area, which is work done per unit volume. That means joule per meter cube. But this is not the required answer, because we need to find total work done. Okay. So how do we find the total work done on the wire? So the work done is, the total energy is, we multiply that work done per unit volume with the volume. So the total work done, so you can say delta W is area multiplied by the volume, and area is that energy, remember. And volume, remember, this V is the volume of the wire, and wire is in the form of cylinder. So area A, which is energy per unit volume, and volume is this is cylinder, so pi r square L. Again, I will be using d square by 4 in place of r square. So r square, remember, is d square by 4. So 61.6 into 10 to the power 6 into pi into d square by 4, and d square by 4 is 5.05 into 10 to the power 3 whole square. This is d square, sorry, not 3, minus 3 divided by 4 into length, and length was given as 40 centimeter in the beginning, and 40 centimeter, which is 0.4 meter. This is the length. Now you multiply all these numbers divided by 4, so the delta W, or the work done, will be 493.5 joule. That's how you find the total work done to break the wire. Question number 17. A mass M is held in equilibrium by a string attached to 2 clamp stand. The force meter record the force in the upper string. The force in horizontal string is P. The angle made by the upper string to the horizontal is theta, as shown. So force F is given, P is given, mass M is given. Meaning given mean we have given a symbol. Angle is theta. The force meter allow force to be measured by a means of Hooke's law. The extension of the spring inside force meter allows the stretching force to be read from the scale. When force applied to stretch spring is 15 Newton, this is F, The extension of the spring is 8 centimeter delta x. Show that the stiffness K of the spring is about 2. So we need to show that K is about 2. So it's a straightforward simple question. F is equal to K delta x. So K is equal to force upon delta x. Force is 15 divided by extension 8 centimeter, of course 0.08. So K would be equal to 187.5 Newton meter inverse. And answer was given in Newton per centimeter, so it is good to make, keep this in 8. So you can have your option, of course, the same, because you can convert it into meter, so it will be 1.87, so it will be 2. So that's how you can prove. So if you put it 8, it is good, because you will have your answer. Okay. When m is equal to 0.55 kg, the value of P is 8.5 Newton. Calculate the value of theta and extension of the spring in the force meter. Now, the force has changed. That is not given, of course, because they put some mass m. Now they have given us mass 0.55 kg and value of P. And they're asking us, if mass is 0.55, the P is 8.5, then find the value of theta and the extension. Okay, so the idea is, in order to find theta, we need to, this is a vector diagram. We have a forces. So we resolve force F into its component. Clearly, this F has two components. This is the tail of the force. So we can draw a horizontal force in this direction. This is X component or horizontal component, or the better way is adjacent component. And this adjacent component will be F cos of theta. And we have a vertical component, which is this. And this will be F sine theta. Clearly, this is mass m, but vertical downward weight W is equal to m into g. Now, if you see the force diagram, F sine theta is balanced by the weight W, which is mg. And F cos theta is balanced by the force P, because F cos theta acting left and P acting right, and this system is in equilibrium, stable. So all forces must be balanced. So vertical force balanced by vertical other force, or upward force, downward force, and leftward force is equal to rightward forces. So F cos theta must be equal to P. Again, this is a typical question of finding angle in case of vectors. Generally, if angles need to be found, and we have two equation involving sine and cos, like F sine theta and F cos theta. The idea is we divide these two equations, so the coefficient gets cancelled. If you divide F sine theta by F cos theta, I'm doing additional step for you. So F sine theta divided by F cos of theta is equal to right hand divided by right hand, mg divided by p. Now clearly F gets cancelled, so sine theta upon cos theta becomes tangent theta, and mg upon p. Clearly you can find theta by taking tangent inverse of mg upon p. Now we have everything. We have m, g and p. So tangent inverse of 0.55 times 9.81 divided by p. P is 8.5 into bracket. So theta, if you do, theta would be equal to 32.4 degree. So this is theta. Okay. Now find the extension. So you know that the new extension delta x as per formula. Now delta x would be equal to force F upon K. K we have found, but we do not have F. That means first we need to find force F, question mark. And how do we do that? We have found theta. You have found theta, you can use either sine theta equation or cos theta equation to find F. It's your choice. I am just using F sine theta, so you can say that F sine of 32.4 into m 0.55 times 9.81, and F is equal to divided by sine 32.5, you make F as a subject. So if you do that, F would be equal to 10.07 Newton. This is the force. Now delta x is equal to force, which is 10.07 divided by K. K we have found 180. What was that? If you go back, 187.5. So 187.5. So delta x would be equal to 0.054 meter, or you multiply by 100, so 5.4 centimeter. It's your choice whether you write centimeter or meter, both are acceptable. Okay, a spherical polyester bead is immersed in oil. The bead has diameter 4 × 10⁻³ The bead is released and moves upward, moving upward through the oil at a constant velocity, that means terminal velocity, so all forces must be balanced. Complete the free body diagram below to show all forces acting on the polyester bead. Remember, the bead is moving upward. So we have up thrust given, and we have two more forces acting because bead is moving upward, so weight would be acting down and drag also acting down. So drag and weight both will act downward. So you can say that this is the free body diagram, free body force diagram, weight and drag acting down. Show that upthrust the oil exerts on the bead is about this Newton. So this is upthrust we need to show. Density is given. If you need to find only upthrust, so upthrust U would be equal to rho Vg. Rho is the density of the liquid, V is the volume of the liquid displaced or volume of the object, and G is acceleration due to gravity. So this is density of the liquid or fluid. This V is volume of the object. Generally it is a sphere, but it can be a cuboid as well, and G is 9.81. So U is equal to, density is 930 into volume, and this is a spherical, and it is required from you that you must remember the volume of the sphere, which is 4/3 of pi r cube. Again, because diameter is given, so I just don't want to waste my time to finding radius, so I will be using r cube as d cube upon 8, because r is equal to d by 2. Okay, So 4 into 4 upon 3 into pi into diameter, which is 4 into 10 to the power minus 3 whole cube divided by 8. 4 upon 3 pi r cube, and then g 9.81. So if you solve all these things, you have up thrust u is equal to 3.1, which is 3.059. Yes, 3.059 into 10 to the power 3.05. Let me just see. Now 3.057. This is not 9, this is 7 into 10 to the power minus 4, and you can round it off and you can say it is 3.1. So this is 3.1 into 10 to the power minus 4 Newton, which is same as the required one. Stokes' law shows how the viscous drag on a sphere is related to its velocity through a fluid. Stokes' law is only valid if the bead is moving sufficiently slowly through the oil. Okay, yes, indeed. State the reason for this condition. The reason is if the bead is moving slowly through the oil, that means the fluid flow or flow of the liquid around the bead will be laminar, because Stokes' law can only be applied. There are certain conditions. The sphere should be small and smooth, small radius, and it should be moving slowly, so that the fluid flow all around the sphere must be laminar. So in order to fluid flow a laminar flow, the bead must be moving slowly. For Stokes' law to be valid, the speed of the bead through the oil must be less than VR, where VR is this. Okay. Deduce whether Stokes' law can be applied to this bead. Okay. Remember, the idea is we need to find velocity of the bead according to Stokes' law. Let's call this speed is V, according to Stokes' law. And then we find velocity, required velocity as per given condition VR. And we compare V with VR. And they are saying that for Stokes' law to be valid, the speed of the bead through must be less than VR. So if this V that we found from Stokes' law is less than VR value, then we say yes, it is valid, otherwise it is not valid. So first let's find the VR. It is direct calculation. You just put the number. Viscosity of the oil is given 4.9. Density of the oil is given in previous question 930. If you see here, this is density. So diameter of the bead, again it is given. So we can find VR. So VR would be equal to 10 times of viscosity of the oil, and viscosity of the oil is 4.90 into 10 to the power minus 2. This is viscosity of the oil divided by density given 930 into diameter of the bead, and diameter of the bead was given in the previous question 4 into 10 to the power minus 3. And there is no square, nothing is there. Okay, fine. You can calculate VR. So VR, if you put all these numbers in your calculator, so VR would be equal to 0.132 ms minus 1. This is the value of ms minus 1. Now we apply Stokes' law. So Stokes' law says the bead is moving with the terminal velocity. Remember the bead. So up thrust acting upward, U, weight acting down, W, and drag force is also acting down, D. And moving with terminal velocity means D plus W must be equal to upthrust. And we know that according to Stokes law, drag is this drag is 6 pi eta r v, this is velocity, plus W equal to u, and we need to find that v here, this v, this is the speed according to Stokes law. So v, make v as a subject, v would be equal to u minus w upon 6 pi eta r 6 pi eta r, that's it. Now if you see, you have everything with you. You have upthrust in your previous part, you have weight given here, this is weight w, and 6 pi constant, eta is a viscosity, which is this is your eta viscosity, and r is the radius, which is half of the diameter. So if you put all the numbers, we have found upthrust 3.1 into 10 to the power minus 4 minus w. W is weight, which is given 1.05 into 10 to the power minus 5 divided by 6 pi 3.14 into eta. Eta is viscosity 4.9 into 10 to the power minus 2 into r. R is the radius. So 4 into 10 to the power minus 3, this is diameter divided by 2. Now again you solve this, so v would be equal to 0.162. Clearly this v is greater than vr, so Stokes law is not valid. So Stokes law is not valid, or you can say cannot be applied for the bead. I hope you got the idea. Okay, that's it for this paper. I hope you understand, and I will just prepare the next video for the unit 2. Be ready for your exam, and have a nice day.